Well, pleasure to be here, and again, thanks for the invitation. I also have never been to Corsica before, and it's been a pleasure so far. I'm going to talk about freezing soil and some aspects of geomorphology that are related to the freezing of soils. And I thought I'd start with a nice image of these needle ice crystals. So this is an example of ice that's nucleated just below the top layer of sediment here, and it's grown out of the soil, pushing these little needles of ice upwards, and it's an example of what might be termed primary frost heave. I suppose there's not layers of lenses. And I was just talking to Gray about this. I have never seen anyone actually do this in the lab or describe it mathematically. But what I'm going to focus on today is, again, this beautiful example of frost heave that Tabor wrote about in 1930. And this is the freezing of a clay that was in a straw box, and as Sylvain mentioned, he very much thanked the company that had donated the refrigeration equipment to him. It happened to have been Frigidaire Corporation, so makes sense. And he did these experiments freezing from the top down. There was something kind of chaotic happening up here, but eventually when things settled down, you get these nice layers of ice that grew sequentially. And each one grows by sucking water up from below, and therefore heaving the ground surface upwards. Yeah. This is, that's hard to see down here, but I believe this is a centimeter scale down here, so I think it's about 5 centimeters across, something like this. Now, this happens in nature, of course. This is a photo that Sylvain showed as well, a photographer with this somewhat unpronounceable last name from Norway. Showing his drive near Trondheim, where the road had developed these ripples as a result of this sort of behavior being uneven from place to place. So this is going to be my focus today, and on Wednesday I want to talk more about, I want to one-up Sylvain's story about pingos by talking about truly large ice lenses, which are glaciers. So this is a photo underneath a glacier, and I'm going to argue that the same physics that takes place here also takes place here, although we don't often get the layers underneath glaciers. And this is a photograph from a paper with freezing in chalk, where something very similar developed as well from a cracking mechanism, and that's responsible for a lot of the debris that you see here in this photo, which is from Canada, from a nice location to go hiking. Okay, so to start things off, I thought I would begin with a video from the Cold Regions Research Laboratory that sort of goes through the process, if it has sound.
As signs of the times go, this is a sure sign of winter in cold regions. The expense caused by frost-damaged pavements affects personal, municipal, state, and federal budgets. Suspension jarring bumps, humps, cracks, collapsed pavements, potholes, and upset posts are all caused either directly or indirectly by frost action in the base course or subsoil. The recipe for frost formation in soils includes 3 primary ingredients: freezing temperatures, frost-susceptible soils, and available groundwater near the surface of the soil. As ambient temperatures remain below freezing, the pavement and the material beneath begin to freeze from the surface down. Ice forms in characteristic shapes called lenses. As the water near the surface is frozen into ice lenses, more water is drawn up to replace it and is in turn frozen. This forming ice expands with tremendous pressure. Since the only direction the ice can push is upward, it lifts the pavement. This deformation causes bumps and cracks in the road surface. In the springtime, as this ice melts from the top down, the water cannot drain through the frozen soil below. There is more water present than the thawed soil can hold. This supersaturation destroys the stability of the base course, reducing its capacity to support the pavement. Traffic loads then break down the poorly supported pavement.
Okay, so the poster session is, no. So these are the questions that I want to address today in one form or another. So first of all, what controls this pressure? Why does the water move to the growing ice? What is it about certain soils that makes them frost susceptible? In other words, susceptible to this sort of damage. And then, if I'm good on time, I will continue with what controls the segregated ice growth rates and how the lenses are initiated. Whoa, don't want to start again. So, first off, I'm going to... Dominic, there you are. Okay, so I've only ever met Dominic on Zoom before, but this is from his paper, from a very nice study. This is published in the Proceedings of the National Academy of Sciences, and this is a figure from the appendix. So I wanted to spend just a little bit of time talking about pre-melting and why this works the way that it does. So we'll think about a system which is everything down here, surrounded by a thermal bath, which is going to keep the temperature constant. So the system in particular involves ice that is separated from an elastic substrate by this thin film of water that we'll call a pre-melted layer. The water itself is connected to a reservoir that is kept at a constant pressure, PL, and the substrate and the ice are interacting with a normal stress, which I've used the engineering, since there's engineers in the room, I'll use the engineering convention of making it negative for compression. Okay? So, to begin with, we want to think about reversible perturbations to this system, and that means that we can't change the entropy of the world, or the universe rather, and we can't change the total energy of the system, of the entire thing either. And so these two statements must be satisfied for reversible perturbations, and since the bath doesn't do any work, we can relate its internal energy to the temperature and the entropy of the bath. And that leaves us with the statement that the change in the internal energy of the system minus the temperature times the change in the entropy of the system must be zero. Okay? So that's one equation. We'll consider next two reversible perturbations. First of all, I want to think about melting a small amount of ice. And then later on, we'll think about transferring a little bit of water from the reservoir into this layer here without doing any melting at all. So those are our two cases. And we'll start with this one, and I'll pepper you with far too many undefined symbols in the next slide. So we want to change the internal energy of the system by melting. That means we'll have this specific internal energy of the liquid times the amount of mass that we've melted. But then we lose some of the ice, and so its specific internal energy is here times the mass. And then we're going to have to compress some things. We're going to need to do a little bit of work. So we take the liquid pressure times the specific volume of liquid times the mass of liquid, and that's added to the system. And we subtract from that the necessary relaxation of the substrate over here. At the same time, the entropy of the universe is not allowed to change, and the change in entropy of the system is the specific entropy of the liquid times the mass minus the specific entropy of the ice times the mass. So it's all very simple, and if you cancel out the masses and stick everything into this equation, you can rearrange the terms, and you're left with these terms over on the left side that involve the normal stress on the ice and the liquid pressure, and then these other terms involving the specific entropies and the specific internal energies. So this is all fine. This is all you need to know to describe the system, but it's not very convenient because how do you measure these things? Instead, it's useful to define a reference bulk melting configuration. What I didn't tell you is that if I took the substrate here and the ice and I pulled them far away from each other, then, so if I made D large, then it would have to be that the liquid pressure and the normal stress on the ice would have to equal each other. Okay? And so doing that, this lets me introduce a reference melting temperature, which Gray introduced already for talking about the definition of what this melting temperature was. But I can substitute that in for both minus sigma NN and for the liquid pressure here, and I'm left with this description of equilibrium. So that's bulk equilibrium. This is my system equilibrium with a very thin film. And if I take the difference between those two things, and then I say that, well, the specific internal energies and entropies of the individual components don't really change very much, I am left finally with the Clapeyron equation, which Gray also introduced in the first place. So there's a difference between the normal stress exerted by the ice and the liquid pressure that is given simply by the difference between the equilibrium temperature and the bulk melting temperature. We've got the latent heat here, and I guess I've used density of ice with a subscript of I rather than S, which we saw earlier in Gray's talk. And the rest of this is the same as in Gray's talk as well. So these densities here are just the inverses of the specific volumes, and the latent heat can be written in terms of the entropies in this way. Okay, so that was perturbation 1, so we want to keep this equation. And now we want to think about a different perturbation where we're not going to allow any melting, but we're just going to take some mass of material from the reservoir and change the thickness of this layer. So if there's no melting that's taking place, the entropy of the system isn't changing. And that means that the internal energy of the system can't change either, because we have to satisfy this equation here. So the internal energy of the system is going to depend on how thick this layer is, because there's an interaction potential between the ice and the substrate that is a function of this thickness. And I'm not going to specify what that interaction is. It's not going to be particularly important for us at this stage, but just that it has to exist. So I can write down the differences between the interaction with a thicker film and with a thinner film. And then I've got my pressure terms here. And saying that this all has to equal to 0, dividing through by delta D, then I have the definition of a derivative here. So that's what winds up on the left-hand side. And Sylvain used the symbol capital P with a subscript T to describe the disjoining pressure. I've used a capital pi instead. But that disjoining pressure, which is the difference between the normal stress in the ice and the liquid pressure, is due to this interaction potential, and it's actually due to the gradient of that interaction potential. So that's what describes this difference here. Now, in detail, that potential could be from any number of complicated surface physics, surface interactions. Van der Waals forces are present everywhere, and this has to do with the induced dipoles of molecules. Often we have impurities, and there's screened Coulomb interactions, so there's many different things that can take place, giving rise to this layer. For our purposes at the moment, all we need to know is that the disjoining pressure that results from them, this gradient, is exactly equal to this difference in pressures. Okay, so that's our second equation, and if we combine them, now we can answer the questions, well, what controls the pressure of ice exerting to cause damage? And just to make things a little simpler, we'll get rid of this term over here by letting the liquid and the ice density equal each other. It's not exactly true, but it's close enough. And substituting this in for the left-hand side of the equation, we're left with this simple expression here. And the ratio of these parameters turns out to be just a little bit over a megapascal for every degree that you are below the bulk melting temperature. So fundamentally, this is what is providing the oomph that is able to wreck those roadways and motivate such wonderful music in that video. Okay, so that's what does it. And you can also answer the question, why does water migrate to supply ice, to supply the growth? If you think about Darcy's law as being a description of what the water flux is through a porous medium, then Darcy's law can be written in terms of a permeability and the liquid viscosity, times the gradient in a potential, which involves liquid pressure, and of course potential energy due to gravity, so due to elevation. And if I wanted to take a specific case, just say that this normal stress here was due to the weight of material that was on top of my ice lens, then I'd use some sort of bulk density times the thickness from the surface down to where I happen to be. And I substitute that into Darcy's law, and I'm left with the heat flux, or excuse me, the water flux being proportional to the temperature gradient. And with that minus sign there, that means that water is tending to flow towards colder temperatures. So just in this very simple case, water is being driven towards colder temperatures as a result of the thermodynamics. There's a correction over here due to gravity, of course, but quite often this term wins out over this term. Okay? Okay, so that's at a very simple level how things work, but it's not very satisfying. It's not going to let us actually make any predictions. Because we need to know something about the soil. So not all soils freeze the same way. And I took some experimental data that I plotted up here, and I should say that I did, you know, I'm liberally stealing data from various papers here, and at the very end of this presentation I will have something in font that is far too small for you to read that will give the references to all the papers that these data come from, okay? So, and if you need more other references, I could provide those as well. But what's plotted here on the x-axis is the undercooling, so that's the temperature depression from the normal melting temperature. So it's cold over here on the right and warm over here on the left. And then on the y-axis, I've got the liquid saturation as a fraction of the porosity. So 100% would be fully saturated, and here we're at 10%. We're not very much saturation at all. And so the different sediments, these sediments, whenever you see these measurements, they tend to come from somewhere where somebody has some fancy equipment like time domain reflectometry or calorimetry. Well, that's not so fancy, but NMR techniques that is interested in freezing soils. And so Manchester silt is not from England. It's from near Dartmouth, where Corel and that video were made. China silt is from Fairbanks, where there's also Cold Regions Army Research Center. There's some wonderful work that gets done in Japan, and so the rest of these are all from Japan. And what you see, basically, is that as you make it colder, depending on which sediment you have, the liquid saturation starts to fall off. The ice saturation would be the opposite of this. So as we're seeing this go from 100% down to just a few percent over here, the ice saturation is going from 0% to make up the difference. Okay? And the important thing is that the different sediments have this transition at different temperatures, and these were all chosen to be fine-grained materials that are frost susceptible to different degrees. Now, in addition to the soil filling up with ice as you make it colder, and that happening over different temperature ranges, that ice actually clogs up the pore space and it makes it harder for water to flow. And so what's plotted over here is the relative permeability, which is defined as the permeability of the soil at that particular temperature divided by the permeability if it was completely saturated with water and there was no ice. So that's how this is normalized. So a relative permeability of 1 would be what you would expect if there was no ice in there at all. So, and unhelpfully, I've changed my axis, so liquid saturation is now down at the bottom. And what you see is that these same sediments start to become very difficult as a medium for water flow as ice fills up the pore space. Even at liquid saturations as high as, say, this is, what, 60% here? You're finding that the relative permeability has dropped down by a couple of orders of magnitude. So it's becoming very, very hard to suck water up. And moreover, although all of these curves have very steep slopes, some have steeper slopes than others, so there's a variation in exactly what the constitutive behavior is of the soil. These soils over here, you can pull water up to a growing ice lens only if the saturation of the ice is really quite minor. In other words, it has to be mostly water. Whereas these other soils over here, it seems like you continue to drag water up even when there's quite a bit of pore ice in the way. All right, so ultimately, frost susceptibility is going to depend upon this constitutive behavior. And if you want to make predictions, what you need to do is you need to measure this constitutive behavior and stick it into a model, and you're off to the races. But I wanted to talk a little bit about why is this constitutive behavior the way that it is. And to do that, I want to go through a couple of arguments that involve some very inelegant modeling. Okay, so this is the cartoon. This is what we expect in a porous medium. We've got a single pore here. It's very idealized. These are the particles. And if it's warm enough, there's going to be nothing but liquid. As we make it cold, the first ice that forms and is stable is going to be a spherical little blob of ice that just fits within that pore. And its temperature is going to be controlled by the Gibbs-Thompson effect that Gray mentioned earlier. If I make it colder still, that ice is able to grow, and it grows by invading the crevices in between adjacent particles. But importantly, it maintains, this is a sort of a blow-up of some region around here, it maintains a thin liquid film that separates it from the particle from the ice. Okay, so this is the geometry that we expect. And with that interfacial curvature effect, so there's the Gibbs-Thompson effect here, and our pre-melting effect, so there's the disjoining pressure there, we can write an equation that describes the geometry of the interface as a function of temperature. Okay? So we can do this analytically for very, very simple geometries, or at least we can approximate it. But you know, this is still an extremely idealized soil over here, but you can imagine that you know, with a random packing of particles, which maybe are not all the same size, that this, trying to describe the interfacial shape inside an agglomerate like this would be very difficult. And so we're not going to do that in a sophisticated sort of way. We're going to do it in a, as I said, a brute force sort of way. Oh, okay. So you're asking if this would affect the mechanical properties of the soil essentially as well. Yeah, it would. Now, the ability for particles to move is going to be frustrated by ice on the other side of the particle where there's also ice. So it turns out that there have been, you know, some careful studies, engineering studies, that have looked at the strength of soils as a function of ice content. And somewhat unhelpfully, some soils get stronger, but it is actually possible for soils to get weaker as well. And the exact reasons for that maybe require further discussion over the cocktail hour as to why that works. Yeah. So the pre-melted film is there because of interfacial interactions that we saw in the thermodynamics arguments. So it was that interaction potential between ice and the substrate. So it's basically, you can think of it as a wetting phenomenon. So if I think in this room right now, we're probably at 40% relative humidity, something like that. And yet, if you were able to interrogate the surfaces of many of the surfaces, say the window over here, you would find a few molecular layers of water, condensed phase, on that surface. And it would depend upon the properties of the surface, of course. But that condensed phase is there because it lowers the overall internal energy of the system, even though we're not at 100% saturation. So similarly, in this sort of a circumstance here, the ice is more attracted to the water molecules, as are the particles are also more attracted to the water molecules, than the ice and the particle are attracted to each other. So that's fundamentally the reason. The details can get complicated, and there are textbooks that are written about exactly that whole subject. But for our purposes, all we need to know is that the films are there and that they're controlled by the temperature and the curvature in this sort of a way. Okay? So if we wanted to get that soil constitutive behavior, we're going to constrain ourselves to thinking about spherical particles. And we want to satisfy this equation, but we don't want to describe the interface itself. So what we can do is just a simple Monte Carlo approach to the whole thing. Basically just pepper the system with lots of random points, figure out what temperature is phase equilibrium favored by ice versus water in each of those points, and then sum them all up and come up with our soil freezing curve. So that's the idea. Now we have, this equation has these two terms here related to temperature. It's going to turn out that when this term dominates is in times when this film thickness is large, in some sense. And by large, we're thinking about more than nanometers, maybe more than microns if in some cases. So basically, as soon as we get away from the particle surfaces here, this term is going to go away. And then it becomes just a question of, for a given point, what is the curvature at which that point winds up being inside ice? And we can have a case where the first ice that is stable envelops a point, and we'll call that pore ice. So if it's less than this radius r pore from the center of the pore, then we expect the curvature of the surface to be described by 2 over the radius of the pore. So that will determine what temperature this point here first experiences the ice phase. Alternatively, we could be right in between two particles, and we could already have this ice, and it has grown into the space between these two particles. It has a higher curvature or a smaller radius of curvature, but it's still a hemispherical surface at this location between these two particles. And in that case, the curvature is 2 over the radius of curvature that we first got to here. And then there's a more complicated case where we have to acknowledge that in 3 dimensions, the curvature is not just 2 over 1 of the radii of curvature that describe that surface, but rather it's the sum of the inverse radii of curvatures, with one of them in this circumstance here being negative. So what I'm thinking about here is that I've got an interface, it looks rather like that one, but there's there's a second radius of curvature because this is an annulus, actually. And so the other radius of curvature here, R2, is negative. And so that's the curvature of this system. So those are the three descriptions of curvature that or equilibrium that don't depend upon the film thickness because we're very far away from the particles. Then, of course, we do have the case where there's films. And now I have to choose a specific interaction potential to describe how the film thickness controls this disjoining pressure. And just for simplicity, I've taken a power law here. This would be appropriate for van der Waals interactions with a cubic power here, so that the film thickness reaches some value, lambda naught, at a disjoining pressure equal to some reference value P naught. I do have to pick these. I haven't measured them. And this is going to be a real failing of this messy little theory, but I'm going to argue in a minute that this film ice is actually not that important for most of the dynamics. It is extremely important in that this is what is generating the pressures, but the dynamics are controlled by water transport and heat transport, and this doesn't really play much of a role when it comes to that. The curvature of this surface here is -2 over the radius of this particle, just for detail's sake. So in Wikipedia, you can look up this fellow Apollonius, and it turns out that there are 2 Apolloniuses that appear in Wikipedia. One of them performed miracles and is basically around the time of Christ, was a competitor for that sort of range of thought. The other one, Apollonius of Perga, actually both of them were geometers, but Apollonius solved the problem of finding tangent spheres to each other. So you can actually just look it up and you can find the answers to all of these curvature, or these radius of curvature problems from Apollonius's work 2,000 years ago. And then you have to pick the right circle, of course. And so fine, that's been solved. This is easy. And we just sum up all the fraction of the points that are in the ice and the liquid at different temperatures, and we can make ourselves a soil freezing curve. And so that's what we've done here. So here's the liquid saturation as a function of undercooling once again. This is data reported by Mariyama et al. For graphitized carbon black, monodispersed 0.12 micron particles. I said that we had to pick a couple of values that we don't really know. These are sort of just coming out of thin air. But I'll explain how that works in a minute. The data points are the points. They've got error bars on them, so that makes them real data. The 2 blue curves we're not going to worry about right now. They're just they're approximations for idealized packings, but this is a random packing. This is a real system. And the red curve here is just the result of our Monte Carlo integration. So it's just a result of that procedure that I just described. And arguably, this does a pretty darn good job, especially when you consider that you could think about these as being fitting parameters, but they only matter down here. They don't matter at all up here, because up here, it turns out that curvature is determining the freezing behavior almost entirely. The amount of liquid that is in those thin films is negligible at low liquid saturations. It becomes increasingly important at high liquid saturations, or excuse me, at high ice saturations, which is way down over here. Similarly here, there's polystyrene data, so a different system, a different size particle, different authors, and the data goes like that. And once again, the brute force model does an incredible job. Since we have our brute force model, we can interrogate, well, what happens if we change our interaction potential? So we can imagine, mathematically, we can decide that there are no films. And if there were no films, then it's this line that comes right down like this. So that is the curvature-dominated regime. And this is just a simple power law that looks like it does a pretty good job over most of the range of saturations. It's defined by two parameters. There's this T sub F, which is the temperature at which the first ice begins to appear inside the pores. And then there's an exponent, which is the slope of this curve in the log-log plot. Okay? Now, if the previous example I had shown you was for picking this lambda naught as 3.5 nanometers. In all of these cases, the P naught value is picked as being 1.1 megapascals. So what this actually is the thickness of a film that we would expect to have on a flat interface at an undercooling of 1 degree Celsius. Okay, so that's how to interpret that. And starting from 3.5 nanometers, increasing the thickness of the film, of course, is going to result in the films pulling us away from this nice power law at lower liquid saturation levels, or higher liquid saturation, lower ice saturation levels. I have to apologize. I often write these things down in terms of ice saturation, and so that's where my mind is. And partly that's, I blame the airport for that. Another numerical experiment, rather than change my wetting parameters or my disjoining pressure expression, is I can change the median size of my particles. And as I get coarser sediments, the curves move down like this, so that the more coarse the sediments are, the less important the liquid films are for controlling water saturation or ice saturation at a given level of liquid saturation. Okay, so that's essentially, I think I would argue that for, at least for random packings of spheres, I've only shown you cases that were monodispersed spheres, but you can do this for polydispersed spheres as well. It's just a trivial change. That the basic behavior looks like a power law, at least up at high liquid saturations. And it's almost entirely controlled by curvature in this realm. Next, I want to talk about how does the permeability change as a result of ice clogging these pores. And rather than go through the details, I'm just going to put up a way too busy slide and say that it kind of works. Okay? Okay, so here we go. So the permeability is dropping because ice is clogging the pores. There's a couple of different ways that you can do this. You can think about, again, picking random points and then just doing a random walk around those points until you bump into a surface. And do that a whole bunch of times at a whole bunch of different points. And then based on that sort of diffusion problem, you can extract a permeability. Okay, so that's what we mean by the obstructed random walk. So it's obstructed not just by particles, but also by little bits of ice that we'll say have the radius of curvature that we would get at a particular temperature. So just following that, just forgetting about the films and only worrying about the particles. The other way we could do this is by modifying a relationship that's often called the Kozeny-Kármán formulation. Sometimes it's called the Kármán-Kozeny formulation. And then there's somebody else's name that gets attached to it sometimes, and I forget who that is. But what that formulation says is that, and it works for spheres, for spherical particles really reasonably quite well, is that if n is the porosity here, and r is the effective size of a particle, that is defined so that if we have a distribution of particles, we add up the cube of their radii and divide by the square of their radii. So if we had monodispersed particles, then this would just be the radius of the particles. Okay? And Kozeny-Kármán finds that permeability goes like the radius, the effective radius squared. And it depends on porosity, of course, but in a kind of a complicated way, it's like porosity cubed over 1 minus porosity squared. And then this constant C is something like 100 or so. It kind of depends upon the shapes of particles, if they're not perfectly spherical and so forth. But it's of a number of about that scale, and it's found to work reasonably well. And we can modify the Kozeny-Kármán relation. When I say that, is that once we start putting ice into the pore space, we just treat the ice as being like additional particles with some particular radius controlled by the temperature. So that modifies how we treat R effective in this expression. And when you go through the algebra, you can write down an equation that looks like this, that just says that the permeability divided by the value that it would have with no ice goes like the liquid saturation cubed, but then liquid saturation is down here as well, so it's a little bit more complicated than that, but it has temperature in here also. So again, using no adjustable parameters, except that we have to pick a value of what the permeability is at fully saturated conditions. These are two sets of data. One is from the Totori dune sand that Watanabe and Asada wrote about, and that we saw earlier on. These are the data points, and the two different techniques for coming up with the relative permeability, which here is written as a hydraulic conductivity, which is basically the same thing in different units. In detail, it's described down here. We do reasonably well in this range of ice saturations. There's a big population of data here that is very different from either of these two curves. And I don't want you to look at that, okay? So that's okay. Here's Manchester silt from near the Carrel Army Research Lab in Hanover, New Hampshire. And again, the data are shown here. There's actually two sets of data. One is for the samples that they collected in a certain size range that I don't recall. The other is the same stuff, but just sieved to have a narrower sized range. And we do very well in matching that data also. So the message is that, well, yeah. Two different ways. So you're testing my memory, but I believe that in this case they used time domain reflectometry. So they used the difference in the dielectric properties between ice and water to figure it out. And in this case, which is from a little bit earlier, I believe that they did a calorimetry experiment. But I'm not, don't quote me on that. I would have to go and actually look at those articles to make sure that that's what they had done. So I'm going to say that I'm satisfied at this point that we know basically what controls the liquid saturation and what controls the permeability. Now, in detail, we don't necessarily have a strong handle on what exactly the surface chemistry is in these samples and exactly how thick those pre-melted films are as a function of temperature or disjointing pressure. But these constitutive parameters aren't very sensitive to that because that only really kicks in when the liquid saturation is quite small. Yeah. Oh, okay. Yeah, no, that's a good point. So we have to so we did the liquid saturation curves, and then we actually approximated them with a power law rather than going through the whole thing. And so if we back up a little bit, well, here, I suppose, well, here, let's go with these ones. I keep changing my mind. Okay, so going with this here, you can see that this power law hits 100% liquid saturation at a finite temperature, right? But actually, when you have a random packing of particles, and this is going to be important a little bit later on, there will be some anomalously large pores that do not fit on that power law very well. There will be a little bit of liquid or a little bit of ice that first nucleates in the really big pores and falls off this power law by a little bit. I think that's what you're seeing here, is that there's still some slight change in the hydraulic conductivity beyond the point where we cut things off and picked our, this is our one adjustable parameter here, is saying that the saturated permeability is this value. Did I answer that more or less? Okay. So back to our question. So what makes soils frost susceptible? Effectively, we need the disjoining pressure that's there because of the interaction potential between the ice and the sediments. We need it to be big enough to generate a pressure that can deform the soil. So we need it to be able to generate large pressures. So we need the ice to still allow some liquid to be present when this temperature is cold enough. And importantly, we need to supply the growth of these ice lenses. So we had Darcy's law written down once again. So water flow has to be able to get to the lenses that are pushing up with this sort of a pressure. So we need water to be present and mobile at reasonably large undercoolings, because we need to deform whatever's up top. And if we approximate the liquid saturation as a power law, and then we don't want to deal with that nonsense here and just call that a power law too, then the constitutive behavior tells us that this saturation, this water saturation, which ultimately is controlling the permeability, is going to fall off when we get any colder than this temperature TF. So we need TF not to be too warm, because then we wouldn't be able to generate much of a stress, but we also need it to be not too cold, because then we would have a hard time moving the liquid as well. And also, this value K0 can't be so small that we can't move water either. So ultimately, we need fine-grained soils that are going to make this value sufficiently cold to do that, but not so fine that K0 doesn't allow significant transport. So there's a sweet spot. If you have something that's very clay-rich and has very, very cold values of this temperature, this characteristic temperature, the permeability will be low, and even though you can generate large pressures, you can't supply the ice growth that you need to cause any significant deformation. Alternatively, if you have sand or gravel, where this might be very, very close to TM, then water saturation is going to fall off so quickly that, again, we can't transport, but this time because the pores are all clogged by ice. All right. So that's the story about my first couple of questions, but I had two more questions, which is what controls the ice growth rates and how are ice lenses initiated in the first place. And I think I can do a reasonable job describing this, but I'm going to give you two alternatives for this. And first I wanted to mention a little bit of history behind all of this. So Tabor famously did those refrigerated experiments resulting in these beautiful pictures. Around that same time, in the 30s, Sweden was expanding their infrastructure into the north, and they were running into troubles with their railways and their roads that they were building. And so there's a wonderful compilation. I would almost say it was a book, but it's just a really long article by Besko, who described a lot of field observations and conditions that would lead to frost damage. Now, fast forward a few decades, Everett wrote a fairly influential paper that based his idea of frost heave on capillary rise. And that idea continues to show up in the literature from time to time, but it has a fundamental flaw, as I'll show in a minute, that capillarity, just that curvature effect and how that affects the water saturation curves. It's very important for controlling the permeability. It's very important for controlling the liquid saturation, but it doesn't generate any pressures that can cause damage. So it's a flawed idea. Gilpin and O'Neill and Miller, working around the same time independently, came up with ideas related to surface interactions, wetting interactions, causing those pressures. O'Neill and Miller actually wrote a complete paper, shall we say, that describes something called the rigid ice model of frost heave, and that's what I'm going to mostly spend our time on, is that model. Andrew Fowler and Bill Krantz made that model tractable with asymptotics. And then the next two developments down here are ones that I won't talk about so much, but I think Gray might talk some about related things to Pepin's work with the morphological instability and how that relates to freezing of binary alloys. And then Rob Stile published a paper about something called geometrical supercooling, which gives an alternative mechanism to the rigid ice model for how lenses can be initiated. And I think that deserves a little bit of time, and I'm going to give it less time than it deserves. And Robert Frost thought about this as well, so before all the rest of those. Okay, so here's our schematic diagram. This is going to be our model to begin with. First off, we want to just focus on what controls the rate of growth of an ice lens that we're going to say is already there. So we haven't worried about how it got there. We're just going to say it's there, okay? So there's our warmest ice lens, or you could call this a pingo up here if you wanted to, possibly. Who knows? What O'Neill and Miller, their big innovation, was to suggest that below this warmest ice lens, which is the one that has access to groundwater down below, below that warmest ice lens, there is ice in the pore space. There's some saturation of ice and some saturation of water, and that this water is able to be sucked up around that pore ice to feed that warmest ice lens. And so this is a blow-up of that region there. We've got it cold up top, so a lower liquid saturation level. There's a temperature gradient, and it's warm down here, so the liquid is completely saturating the pore space down at the bottom. There's going to be water that's flowing up to supply the growth of this ice, because mass balance has to be considered. And if we've got ice that's moving up at some rate v here, we've got to get water up there to supply that growth to allow this to continue to happen. And that water flux is going to depend upon the permeability, which was our second constitutive law. That is an excellent question. So, this is another piece of brilliance by O'Neill and Miller, is what they recognized is that in this model, at least, this fringe is meant to be all connected, so it is all moving up at the same rate. And what has to happen is that as the ice moves up, it's going to have to melt at locations like this, and it's going to have to refreeze at locations like this. And this is a process that's referred to as regelation, which just means refreezing in regular English. And it's something that was discovered, I think the first paper I've seen written about that was in the 19th century by a guy by the name of Bottomley. But there's a wonderful analysis by John Nye from the year I was born, actually. It's a long time ago. But not as long as some people's. So you can look that up. Yeah, just looking at all the characteristics of that. And it turns out to be important for deformation of glaciers as well, when they slide over small bedrock obstacles. So it's a well-known phenomenon, but this is required. We need to, and it is an assumption as well, that all of this ice is moving up at the same rate. And it's possibly a flawed assumption, but we're going to go with it for now. Okay, so in this model, this fringe, all connected, it's going upwards at some rate, to some growth rate that is the same as the rate at which the ground surface is being heaved up. And it's supplied by Darcy transport that depends again on this permeability. And an important assumption that O'Neill and Miller makes that's connected to this business about all this ice moving at the same rate is that it is assumed that there is no deformation of the particles within this frozen fringe or down here in the soil down lower, so that all the porosity below this lens is just a constant, okay? And there's no compaction taking place in here. So when Sylvain and other people talk about colloidal freezing, that is an important distinction in that in those systems, you can absolutely not ignore compaction. In this system, possibly you can, or at least I'm going to, okay? As a corollary to that, we'll also assume that these two constitutive properties, the liquid saturation and the permeability, don't depend on how fast I'm heaving. So in other words, they're just functions of temperature in each other. Okay? Okay, so mass balance means that the Darcy flux through here, the ice density times the water transport rate, the Darcy transport rate, has to balance the rate at which the ice is moving up, which depends on the ice density, the porosity, which I said is constant, and the ice saturation in the space, which is 1 minus the liquid saturation. Okay? So that relationship is going to give me a relationship between Darcy flux and the rate of heave. Okay? The next thing that I want to talk about is the force balance on this rather sort of contorted ice surface. The force balance has 3 components. If I just think about the force over all of the ice that is connected to this lens. And those are gravity, and then water pressure that's pushing up, but I'm going to cheat a little bit just for convenience, and I will subtract off the hydrostatic water pressure and just work about with the hydrodynamic pressure, which I've unhelpfully given the same symbol. Okay? So, just for convenience. So, if water is flowing up, that means that water is flowing against gravity, and so that the water pressure up here is lower than its hydrostatic balance. So, effectively, it's being sucked up, and the net hydrodynamic pressure on the ice is actually downwards. Okay? And that's only because I'm taking the hydrostatic part and throwing it into the gravity term. And then finally, I've got the net disjoining pressure between the ice and the particles throughout this entire thickness. So, gravity is simple. The hydrodynamic pressure is pretty simple too, because we have this relationship between Darcy velocity and heave rate. And I'm not going to put down Darcy's law again, but we've seen that also. So down here at the bottom, the net hydrodynamic force per unit area can be written as the hydrodynamic pressure at this level at the bottom of the fringe, which I'll call location ZF, plus a bit that relates to the velocity of heave. So the faster I'm heaving, the more viscous dissipation that there is, and it's going to increase the net downwards hydrodynamic force on the surface of this lens. Okay? So the terms that wind up inside here, inside this integral, involve the liquid saturation, because it controls the ice saturation, so it's this term right up here. and the permeability, which is going to vary throughout this thickness here because the ice saturation is varying because the temperature is varying. Okay? So in particular, the permeability is relatively warm, or relatively high down here where it's warm, and it gets increasingly lower as we get up towards the lens boundary. Okay, the disjoining pressure is a bit of a mess, okay? And so I've cartooned it out here. The disjoining pressure, again, it's the force due to that interaction potential, which I don't even know what the film thickness dependence of it is, but in any case, it's there, and it's controlled by temperature. But here, the disjoining pressure, the particles are pushing up on this little piece of ice, but they're pushing down on that little piece of ice. And they're pushing up on that piece of ice from this particle and down on this piece of ice from that same particle. And I need to do a surface integral of the disjoining pressure over this entire surface. And so at this point, I think it's important to take a diversion. So here's an easier problem. We've got a single particle sitting in ice. We could think about this as one of Sylvan's particles, for example. And it's in a temperature gradient, so on the cold side of the particle, the film here is relatively thin, and we have some particular disjoining pressure that will be, you see the size of the arrows here is relatively large. Because the two surfaces are close together, and so we expect them to be interacting strongly. On the warm side of the particle, the film is going to be a little bit thicker, and the interaction is going to be a little bit less. Okay? So on balance, this disjoining pressure around this particle is going to vary according to the temperature and to the radius of curvature of the surface, which is just controlled by the particle size here. And this is a problem that we can integrate fairly straightforwardly. We can just integrate the disjoining pressure around this entire surface, calculate a net force, and it will be pushing this particle downwards. I don't really care about the answer to this problem, so I'm not going to solve the problem, but I will calculate this force. Of course, the force on this particle has to be balanced as well. Gravity is probably not going to be important if this is a small enough particle. But where the resistance to this downwards force is coming from is from viscous dissipation as water is formed here by melting and refreezes up at the top. Okay, so this is that regelation problem that I alluded to earlier that is important within the fringe. So if I want to calculate the force, I want to calculate the integral over this entire surface. The surface has, I've drawn it here with an outward normal so that I have to put a minus sign to calculate the force. I have the disjoining pressure in terms of temperature and curvature. I can just substitute this equilibrium relationship in here, and I can split the integral into two terms, one involving temperature, the other involving curvature. And then there's a wonderful result that the integral of curvature over any closed surface is 0. So this term actually doesn't contribute anything to this integral. This other term here can just be turned into a volume integral if I take the gradient of the interior parts. And it tells me that the net force pushing this particle downwards is just this ratio of terms here, that 1.1 megapascal per degree C, times the integral of the temperature gradient over the volume, or if the temperature gradient is constant, as it would be in this situation, I can just say that it's the mass of ice that is not inside where the particle is, times this potential. So it looks a lot like a buoyancy force. But whereas Archimedes, so going back to the Greeks again, Archimedes' buoyancy force comes from the volume of displaced liquid when you float. This is coming from the volume of displaced ice that would lower the chemical potential or the free energy of this system if it were to replace the particle in the water. Okay? So that's great. The result itself does not depend upon the shape of the particle. This integral relationship here is completely general. It just depends on the integral of the volume. And whereas, whoa, wrong direction. Integrating over the surface is nasty. I already have a relationship for the ice saturation as a function of temperature, and so I can integrate over this surface, turn it into an integral over the volume of ice that is not below the, that is taken up by particles underneath the ice lens. And then I can go a little bit further as well. Why would I want to integrate a gradient in temperature over space? Why not just integrate over temperature changes instead? So I'm left with a fairly simple expression that describes what the net force is as a result of all these interactions in my contorted space. And importantly, it just depends upon this constitutive behavior, once again. All right. So this is how we make the model. What controls the segregated ice growth rate? Ultimately, Gray is going to tell you that, because basically the rate of growth of the ice down here depends upon a Stefan problem. It's really all about heat transport. So we've already seen conductive heat transport and latent heat release. And that is a big part of the answer to what controls heaving rates. Except that there's a wrinkle. Whereas in a regular Stefan problem, we need to worry about the jump in heat flux across the solidification front. So in a place like this, in this problem, not only do we not know the location of that solidification front, the ice lens boundary, we also don't know the location of where we finally lose the ice, where we get warm enough to reach this temperature. Okay? So that force balance condition winds up giving us a constraint that relates to the velocity or the heave rate, which is our additional boundary condition on this problem that is necessary to come up with a solution. So I'm not going to belabor that point any further, except just to say that there are different regimes in which one can live. One can be in a regime in which the system is steady, so that the lens stays at the same constant temperature, and the thickness of the fringe stays at the same constant thickness, and we just grow forever. And possibly that may be how pingos work. Who knows? But that only happens if the rate at which energy is being pulled out of the system is in some sense balanced by the rate at which water can be supplied to the system. Okay, so the force balance condition and the heat balance condition need to be delicately balanced in order to maintain just a single lens growing forever. And what you see here is that didn't happen in this case. We have multiple lenses. And what has happened then is if the freezing and the heave rates are mismatched, then it's possible, in particular if the fringe is able, if the fringe is able to get thicker through time, that I can nucleate new lenses. So here I've got a frozen fringe here, and I want to know when am I going to nucleate a new ice lens. And so I can go back to thinking about force balance conditions. And this is following again from O'Neill and Miller, the idea that when the particles at some level, call it Z here, no longer feel any force between themselves, then I've unloaded those particle contacts, and ice can invade in the space in between those particles. So in this realm, between the base of the warmest ice lens that's growing and the base of where the last pore ice disappears because it gets too warm down here. That effective stress, supported by the particle contacts, has to balance any difference between gravity pushing down, hydrodynamic pressure also pushing down, and the net disjoining pressure between particles underneath that level. So I can calculate that force balance as well, and it just involves me making a different sort of integral. And rather than show you that result, what I'll show you is a numerical prediction for one particular instance of how ice lenses get initiated. What's plotted is the effective pressure between particle contacts, normalized by the effective pressure at the bottom of where there is no more ice any longer, so normalized at this location, ZF. And then height is normalized in a way that I didn't even bother to put on the slide. But in any case, the qualitative behavior is what we're after. What happens close to the bottom of where pore ice is that the ice is pushing against the particles, and it's still connected to the ice above, so it's able to transmit forces up. And the particles in this regime are feeling less effective stress or bearing less of the weight of the overlying material than they are in the unfrozen sediments just beyond that boundary. And as I get further away from that boundary, because the ice saturation is increasing and it's getting colder and the particle ice forces are getting stronger, the effective stress between those particle contacts is dropping further still. However, if the fringe gets too thick, what eventually can happen is that the permeability gets so small up here where it's cold that it's taking a lot of the fluid pressure gradient that is driving water transport needed to satisfy mass balance needs to get very steep. And that results in actually making the particles have to bear more and more weight. They get effectively sucked together. So the curve takes this characteristic sort of a shape. If this distance here were relatively thin, this would turn around and the effective stress would never reach zero. But there is a time, once you get thick enough, that the effective stress at some new location can go to zero. And in the O'Neill and Miller rigid ice model, that is the location where we say that a new ice lens can be nucleated. So that's the idea. Putting this in a model, again, this is Colin Meyer's work. You can make a numerical model that will describe this sort of behavior with, here we plotted porosity, where we say that the ice lenses here have no porosity, or have no nothing but ice, actually they have 100% porosity, and in between the ice lenses there's some finite porosity. So you can solve that problem, and it's been done in a couple of different ways. Andrew Fowler did some work with his student Noon as well back in the 90s. If you want to analyze the problem a little bit further, you can look at things, metrics like the spacing in between ice lenses, so the thickness of the fringe at the point where a new ice lens is nucleated. That's this distance L, and the model, the numerics give us this blue line, or excuse me, the numerics give us these spots, rather, and you can do a scaling analysis and find that thickness goes more or less like 1 over v if the velocity is fast enough, but when it gets slower, then the ice saturation comes in, and so forth. So this is just a comparison of a numerical model to itself in some sense. Not very satisfying, but this is what gets done, increasingly. We can try to compare against data. So there's a number of papers that show images of ice lenses, and we can look at those images and we can extract a lens spacing, and based on the experimental conditions that they describe, we can infer a heat flux. So I didn't put error bars on here, but there probably should be some pretty big ones. And it kind of follows the theoretical prediction, sort of more or less. But, you know, it's geology, so you can accept large errors and say, oh, it's the right order of magnitude, and we're great. Looking in more detail at a particular experimental image, just to show the warts. This is a paper by Wang. This is their image of ice lenses. We needed to plot a lens spacing. They're not those nice planar ice lenses that Tabor managed to grow in the end. So there are big error bars on here. The simulations kind of go through the data, but I think you would say that the data that supports this treatment is not overwhelming. I mean, there is room for other interpretations as to whether this ice lens nucleation model actually makes sense. And that gets me to thinking about our constitutive behavior once again. This was just a particular example of the graphitized carbon black. This is what the model is using to describe the ice saturation. I told you already that we weren't going to do a very good job at really low liquid saturations because the films are going to start to become important and change the behavior. But I also told you that I didn't care about this because the water is basically not moving at that stage anyways, so we don't really need to worry about it. We're really interested in the behavior when the temperature is warm enough that there's still lots of water around and able to flow. I wanted to draw your attention to this gap here, though, that lets us know that there are big pores, as mentioned earlier, that seem to fall off the power law, and the idea of a one-dimensional continuum treatment that the water saturation or the ice saturation is just supposed to go continuously with Z without any changes laterally because we're doing a one-dimensional problem, that's probably wrong. And in some nice work by Rob Stile, Dominic's advisor, they did experiments in freezing colloidal soils, so with some compaction. And from the experiments, what they thought that they saw was little needles of ice that appeared to be possibly shedding off side branches. And they explained it in this fashion, thinking that if there's an anomalously large pore, if the ice can get down here and can actually just start pushing the particles out of the way on either side, then that flaw can expand more like a crack, rather than like this rigid ice model requires, where I'm not allowing any deformation anywhere except when I form an ice lens spontaneously at a given level. So this is a different mechanism for ice lens and nucleation. And it's referred to as geometrical supercooling by Rob Stile. To my knowledge, it's never been put into a complete model that predicts lens spacing and so forth, but it's a similar thing, yeah. Yes. I would say that those are two different effects, but I'm not saying that they're not related. So I guess what I would say is that what is clear is that the void ratio in a granular medium depends upon the effective stress, right? So if you have a dense granular medium and you change the effective stress, you expect to change the void ratio. What you are describing is if there's motion that you're going to change the, like a dilation sort of type thing. Absolutely, yeah, I would accept that. It's basically the same as that then. So all I need is my ice is pushing in all directions against the particles that are close to it. If there's no ice in the pores on the other sides of those particles to push back, then why wouldn't the particles just move out of the way? And that's the idea here, so we could get a crack forming. Now, this turns out to be important for deforming cohesive materials, as I hope to talk about on Thursday, I think. So the answer to this question, I would say that I've gone through the model of how the sediment contacts can be unloaded by stress transfer through the fringe. But there's this other mechanism as well, that it could nucleate in large pores and then propagate as a crack, exactly like this. And I think that gets us to poster time. So I focus here just on this problem. I want to apply it on Wednesday to thinking about some problems underneath glaciers. And then Thursday, I think, talking a little bit about crack formation in cohesive materials as well. So I'll leave it at that.